discuss about graph data structure. So in the previous class, we have seen introduction to graph and its application, and we have seen how to calculate the shortest path from one place to another. So what does a graph consist of? Edges and vertices and path. So what are the types we have seen over there? We have seen cyclic graph, acyclic graph, weighted and unweighted, directed and undirected. So there is another type of graph called as connected graph. So connected graph in the sense, if there is a path from one vertex to every other vertex in the graph, then we call that particular graph as connected. So if we take any vertex, if there is a path from that particular vertex to all the other vertices in the graph, then that graph is considered as connected graph. So can I consider this graph as connected graph?
No.
Because there is
no
yes or no?
path.
Yes, it is a connected graph, right? See, from A to C, I have a path. Path is different, edge is different. So
from A to C, there is no path.
There is no edge. Paths, we have a path. So from A to C, we have a path. So this is a connected graph. This is also a connected graph. Again, this is a connected graph. This is also a connected graph. So connected graph is an undirected graph. If the graph is like this, so what type of graph it is?
Directed,
this is directed. So as you like, when you look at this figure, you can say it is directed graph. So if in a directed graph there is a path from one vertex to every other vertex, then we call it a strongly connected graph. So you understand the difference between what is connected and strongly connected graphs. So with this connected graph, we can construct spanning trees. So can you explain what is spanning tree is?
So spanning tree, the number of edges, the number of vertices connected with the minimum number of edges is known as spanning tree. And the use of spanning tree is not to repeat the same vertices or to avoid loops in a connected graph. So examples of spanning trees are C and A, B, C. Can you draw some other examples?
Oh. This edge. Oh. Yeah, this is enough. Yeah, you remove this edge. So these are some of the spanning trees that we can construct for this particular graph. So have you ever wondered how many spanning trees we can construct for a given connected graph? So how many spanning trees can we connect for a given
with this formula n power n minus 2.
Someone check it.
Every spanning tree consists of n minus 1 edges.
So someone check if that formula is correct.
So total number of vertices is...
So you can take 3 vertices. So that will be easier. So take 3 vertices. It will be easier for me to draw a graph with 3 vertices.
So there's total number of vertices is 3.
3.
So n power n minus 1 is 3 power 3 minus 1. 3 power 2.
3 power 1. Oh.
Mm-hmm.
N power n minus 2 is the formula.
So 3 power 1 is 3.
So draw a graph with 3 vertices. Like A, B, C. C. Now draw the spanning tree for this particular connected graph. So check if this formula is correct. AB, AC. C, AB is one edge, AC is another edge. AB is one edge, AC No. So A, B is one edge, A, C is another.
So there's total three numbers.
So for this particular graph, we have constructed three spanning trees. So this formula is correct. See how many edges are there? In each spanning tree, we have edges.
Edges
so
two.
We have two. So when the number of vertices is 3, we have n minus 1
N
edges.
minus 1. 3 minus
So
1.
in any spanning tree that we construct, the number of edges will be equal to number of vertices minus 1. So to find the minimum spanning tree, we need a weighted connected graph. Only using weighted connected graph, we can find the minimum spanning tree. These are this is one of the examples we are using a weight. So these three are the minimum spanning tree. We'll find the minimum value for these three trees. We should find total cost for each tree. While comparing these three, while comparing these three trees, this is the minimum spanning tree because it is the minimum cost. 8. So here we have two algorithms. That is, one is Kruskal and one is Prim. So Kruskal will arrange the vertex edges in ascending order. And to avoid the loops, we go with the recipe and we'll avoid the loops. And in Prim's, every vertex should be connected to its equal vertices. These are two algorithms. So as we have seen, the need for spanning tree is to avoid the loop so that we need not repeat the same vertex again and again. So to avoid the loop in the graph, we go for spanning tree. So and the spanning tree with minimum cost is called as minimum spanning tree. So for a given vertex, we would have constructed more than one spanning trees. So the one with minimum cost is called as minimum spanning trees, and we have two algorithms. One is Prim's algorithm, and the other one is Kruskal algorithm. So Prim's is almost similar to Dijkstra's algorithm. In case of Dijkstra's algorithm, you will have a single source. So from that single source, you will calculate the cost for all the other vertices. Whereas in case of Prim's algorithm, you will calculate the cost based on the vertex that you are visiting at that particular time. So the main vertex we are visiting at that particular time, from that vertex you will calculate the distance. That is the working of Prim's algorithm. So Kruskal's algorithm works by sorting the edges in ascending order of cost. Ascending order of cost. So you will include the edges if it does not form a loop. If it forms a loop, you will discard that particular edge. The final resultant tree will be your minimum spanning tree. So it is common for both the algorithm. Irrespective of which algorithm you are using, the minimum spanning tree that you are going to construct will be the same.